Okay, continuing on from last time, I have now the stoichiometric equation here. Now, one of the things I notice already is I say to myself, well, I don't really have a way to get any more information except knowing that the mass in here is 1,500 kilograms. I don't, and I know this is stoichiometric, I know this is 1,500. So now I'm faced with the fact that I have to convert these known number of atoms, maybe with a factor times this equation, to mass. So, okay, let's go ahead and do that. Okay, what I have here is I've written down some factor times the mass of the stoichiometric reactants equals 1,500 kilograms. And if I convert each one of those to the mass that it corresponds to, so we've got 12 times aluminum, and one mole of aluminum is 26.9 grams, and then we use calcium to convert to the mass of 1 mole of calcium. And then what we end up getting is that our F value, this factor, is 1.11 times the stoichiometric mass. So there's some factor out here, 1.11. So this becomes our new basis. Okay, let's go back to the problem and figure out what it was that we wanted to find. Here's a stoichiometric process. What masses of aluminum and lime should be added to the reactor? So we can get that by multiplying this F times this and F times this. And what do we get? Okay, in doing this, I realized I committed, again, a cardinal sin of forgetting to keep track of the units. So these are grams here. These are grams per mole. Grams over here, kilograms over here. So this answer is off by 1,000. So I multiplied in this factor of 10 to the 3 here. So to get aluminum, I take the 1.1 times the grams that I have of aluminum, the stoichiometric amount here, times 10 to the 3rd. And this is what I get for aluminum. And knowing I have 2 sig figs, 360 kilograms of aluminum. For calcium, I do the same thing. I use that factor and then 10 to the 3rd, make sure I account for the units. I multiply it by the stoichiometric amount of CaO that I have here. So I get 186 kilograms of calcium oxide, or 190 kilograms calcium oxide. Okay, what is my next question? So that's this part of the question over here. What mass should be expected from it? Well, to get the mass, let me make this a little smaller. I'll put this over here. The mass is working with these set of numbers here. We're going to need to know the molecular weight of NB3Al. Okay, using the molecular masses of the component and our factor F here, I know that I have 2 moles in the stoichiometric equation of NB3Al, and that 1 mole is weighs this much, 3 times the mass of the NB atoms and 1 times the mass of Al. I got this all kind of crunched up here, and what I got here is 680 kilograms for this mass. What else are we trying to find out here? So if you run the reactor with 40% excess lime, what would be the resulting batch composition? Now this is a good question. So if we add excess lime here, what do we get out here? Well, normally we think of Le Chatelier's principle. If we have an equilibrium reaction, if we put more on this side, it pushes the reaction to the right. But one of the things that Le Chatelier's principle doesn't sort of make explicit is that it assumes that you have excess of these others as well. In our case, if we only change this lime and we don't change the other two, then the aluminum and this niobium oxyfluoride become the limiting reagents. So if we just add excess lime, we're probably just going to get the excess lime over here. So we'll get the same output because we don't have any more reactants to push the reaction to produce more of these products. So we'll end up just getting the same thing that we had before with 40% excess lime.